In the previous lecture, we studied how the Catmull-Clark subdivision surfaces algorithm works. In this lecture, we'll see a few more details about the same algorithm. Other important properties of Catmull-Clark subdivision surfaces algorithm are as follows. When the control points form a simple grid topology as shown in this figure, the surface tends towards a bicubic B-spline, a standard kind of surface that is used when smoothness is required. So, Catmull-Clark algorithm gives us smooth surfaces. However, unlike other techniques for getting such surfaces such as NURBS, which are computationally intensive technique, the technique naturally tends to other topologies. That is, the Catmull and Clark subdivision tends to other topologies as well, which gives 3D modelers much freedom. One of these freedoms is the properties like texture coordinates can be smoothly generated in a simpler way, exactly the same way as we calculated the vertex positions by averaging them with the same weights during the subdivision. So we can extend the texture coordinates in exactly the same way as we calculated the next set of vertices. Counting the number of new vertices for open surfaces after one subdivision step can be a bit confusing. For closed surfaces, the counting is easier and more intuitive. Now here is an exercise for you. If you haven't gone beyond this slide, try to answer these questions. After one subdivision step, how many vertices are there in a cube? And after two subdivision steps, how many vertices will be there in a cube? Now verify your results using Blender. In Blender, you have an inbuilt Catmull and Clark subdivision algorithm. Use that to divide a cube once and then twice and then count the number of vertices and verify your answer. In the next slides, I'll show you the answer to these questions. Now let's try to answer our first question. Starting with a cube which has 8 vertices, 6 faces and 12 edges, how many vertices, faces and edges will we have after one subdivision? Now here we have performed one step of subdivision. So there are 26 vertices now. So our vertices, new set of vertices is basically the sum of the previous vertices plus the previous faces and the previous edges, because there is one vertex for every vertex, one vertex for every face and one vertex for every edge. Hence we have a total of 8 plus 6 plus 12 is added up, giving us 26 new vertices. The number of new faces is 4 times the previous faces, because we have now 24 faces, and the number of edges that we have after one subdivision is 2E0 plus 4F0, and that's 24 plus 24 is equal to 48 new edges. E0 and F0 and V0 basically stand for the number of vertices, faces and edges when no subdivision is performed. So we can generalize this using n instead of the 0 and 1 values here. Our general equations would be like this. At any subdivision step n, the number of vertices would be the sum of the previous vertices, previous faces and previous edges. The number of new faces would be 4 times the previous number of faces, and the number of new edges would be 2 times the number of previous edges plus 4 times the number of previous faces. So now we have general formulas as to how many vertices, faces and edges we will have after n subdivisions. Thus, after 2 subdivisions, if we plug in the formula, we will have the number of vertices equal to the number of vertices in the previous step, number of faces in the previous step, and the number of edges in the previous step, which is V1, F1, E1, 26 plus 24 plus 48 is equal to 98. Now we can calculate the number of vertices for any iteration n, and the same goes for the number of faces and edges. As the Catmull and Clark subdivision surface method constrains the surface to be smooth, the cube would approach the shape of a sphere after a few subdivisions. The result above can be verified in the software Blender. So I encourage you to practice this in Blender and you'll see that after a few subdivisions, your square will tend to your cube will tend to become a sphere. So this is after one subdivision. This is after two subdivision steps. You can see we are already getting a ball shaped structure. And if you were to use texture mapping on top of this, perhaps this many few vertices would be sufficient to model a soccer ball or head of a person and so on.